All right. Good morning sa mga early birds for today. Prince, Neo, Neil, Victor, and Denmark. Happy Thursday. We're almost there sa weekend. Though hindi masyadong magandang weekend ko because meron akong mga research meetings ngayong weekend. So nothing really much to look forward to. Pero anyway, I still have Sunday and probably Monday. So I hope you guys can find some rest this weekend. Lalo na ngayon, week 11 na tayo. Patapos ng week 11. So patapos ng SEM. Alam niyo naman, yung mga instructors nyo, kapag patapos sa yung SEM, naghahabol na ng outlines, naghahabol na ng topics, and then naghahabol na rin ng requirements. At yun yung isa nating titingnan kasi magpapa-homework ako ng isa sa inyo. So malulungkot na naman kayo kasi hindi na nahimik, quote-unquote, ang 191. Meron tayong homework for this week. Ang deadline pa naman ay next week. Probably I'll put it at Thursday next week, 11:59 p.m. But more on that later. Just a quick update. I hope you have seen my comments. I have already graded the problem set. Although napansin ko ay hindi pala kayo gumawa ng groupings kay Canvas. So ang ginawa ay meron lang kayong isang designated member who uploaded the file and everybody else wala nang ginawa. So that's okay lang naman pero I expected na gagawa kayo ng group kay Canvas tapos para yung paper ay mag-appear o yung submission ay mag-appear sa bawat isa. So when your group leader or somebody from the group submits a homework, kung naka-declare yung grouping nyo kay Canvas, lahat ng members ng group magkakaroon ng submission kay Canvas. But I think that didn't happen, which is fine. Minano-mano ko na lang yung encoding ng score. So I already returned all problem sets. So if you want to get the feedback that I sent or to know why that is your score, please talk to your group leader kung sino man yung nag-submit. So may access siya dun sa graded problem set. Yung mga nag-submit via email, I replied to the member who submitted it to me. So hingi na lang kayo ng kopya sa kanila, right? But your standing is already updated in Canvas. I already also graded homework number 5, I think. So should be there. So wala na akong utang sa 191. Tinapos ko siya kaninang umaga kasi para Math 151 at Math 174 na lang yung problema ko. Ang sakit sa mata ni Canvas kasi meron siyang notif, may red number nakalagay sa kanya ay 339. So ibig sabihin I have 339 more or less papers to grade minus yung lab exercise ng 174. So kailangan ko nang magbawas. So ngayon ang sa mga susunod na araw yung 174 naman saka 151 yung pagtutuunan ko ng pansin. But yeah, that's the quick update. Ano yung question? What is this about, Prince? Paano yung graph sa interval negative 1.25, 1.25? Ito yung graph ni phi, yung PSF. Yeah. Dapat ay dalawa yung spike. Kasi if you remember, it's non-zero yung meron kang component na phi sub 0. Kasi alam natin yung phi sub 0 will be equal to some value, non-zero value kapag ka si x ay between, if I'm not mistaken, negative a to a, right? Tapos kapag ka zero na siya elsewhere, right? So if I'm not mistaken, this is how we define the building piece for our PSF, si phi sub 0, right? So ang A nyo ay 0.01, so napakaliit nung spike. So baka dun sa pagkaka-plot nyo ng window, one possibility is hindi nakita dun sa graphics yung pangalawang spike, right? Kasi alam natin dapat non-zero siya sa negative A to A. Asymmetric yung negative 1.25 to 1.25. So meron kang isang spike dun sa gitna that will happen from negative 0.01 to 0.01. So magkakaroon ka ng spike. Tapos there's another spike from, I guess, negative 1.01 to to negative 0.99. So napaka nipis na spike nun. So and I guess Prince, you got that in the in your problem set. Ang kulang kayo ay yung spike dun sa kanan. Number one, you should have anticipated, or you would have you would have known that something is wrong. When you look at the graph, bakit ganito? Alam ko si Phi, hindi pala to si Phi, tama, si Phi Sub-Zero to. Si Phi, dapat tatlo yung spikes kasi meron siyang tatlong maliliit na interval kung saan non-zero yung value niya. So hindi na display yung yung pangatlong spike kasi baka masyadong manipis yung yung graph. Hindi siya nakita dun sa figure window. So one thing that you could have done is probably maximize the figure window. Baka lumabas dun yung spike. Um, and I guess you could have plotted it in two separate sorry, you could have looked at separate graphs kasi halimbawa I think it was Denmark. Napansin niya na, oo nga 'no, kulang ako ng isang spike dun sa graph ni Phi, pero napansin ni Denmark dapat tatlo yung spike. So ang ginawa ni Denmark, ginraph niya or nag-zoom in siya. So sinabi niya na posibleng merong nangyari dun sa resolution ng figure o dun sa size ng figure, hindi masyadong nakita yung napakanipis na spike. So ang ginawa niya, pinlot niya, hinanap niya yung plot dun sa mas maliit na interval. So instead na negative 1.25, 1.25, pinlot niya yung graph from say near the tail near the tail end. Tinry niya halimbawa from 1 point from 1 point from 1 point saan ba ipa-plot? Halimbawa, 0.98 to 1.02. So sa 0.98, 1.02, mas maliit yung x interval kung saan magpa-plot ng graph si Matlab. So malamang kitang-kita yung magiging spike. So that merited some deductions for actually hindi lang sila Prince. I think there are 2 or 3 more other groups na ganun yung naging problema. So, nagka-minus kasi dapat napansin nyo na something is wrong. And then you should have looked for a remedy like what Denmark did. Yung iba naman, ang ginawa nila, binago nila yung scaling. Kasi nakita nila na baka naman pwede natin paglaruan yung scale para hindi ganun kanipis yung graph, yung spike. So para ma-read pa rin siya nung figure window. And what others did, minaximize nila yung buong figure. So it's a more of a rectangular rather than a square graph. So na-stretch yung x-axis, mas lumabas or mas nag-appear yung spike. So yeah, that's one thing that you could have done. Hold on, guys. And then that reminds me of another comment that I have, pero this time sa homework number 5 naman. Remember I asked you kung bakit dapat in-expect na natin na magde-deteriorate yung accuracy ng estimate dun sa later times, dun sa temperature, all right? Pag ginamit natin yung forward solver. Remember our forward solver is we have U upper J plus 1. Sa ano naman to? Sa heat diffusion, U upper J plus 1 equals U upper J plus V upper J, all right? For J going from 0 to capital N. Tapos sabi natin si U sub 0 galing sa initial condition, si U upper 1 siya yung temperature at the first time step T sub 1, and we expect very good results there as long as the convergence criterion is met, that delta T over delta X squared should be less than 1/2. And then pag nasa U sub 2 ka na, medyo expect mo bababa yung accuracy, all right, kesa kay U upper 1. Then the accuracy will again is expected to deteriorate when you are at U upper 3 and so on. So as we go forward in time, we should expect deterioration of the accuracy of the estimate. And most of you, or actually all of you, got the idea that the problem lies in the fact that para makuha mo si U upper J plus 1, ginagamit mo si U upper J. Tapos si U upper J, kapag kasi J ay greater than 0, si U upper J ay galing na sa isang estimate. or actually estimate na siya, right? It's not the exact value. This is not the temperature profile at time t sub j. Estimate lang natin to para sa temperature sa time t sub j. And you're using this estimate in this equation, and so u upper j plus 1 is not just tainted by the theoretical error brought about by the discretization of the partial differential equation. So alam na natin we're losing accuracy kasi yung continuous model, which is the exact one, pinalitan natin siya ng discrete. So meron kang theoretical error o discretization error na tinatawag mula dun sa proseso ng pag-approximate ng isang continuous problem like a partial differential equation by a linear equation. So meron na tayong na-lose na information or na-lose na accuracy from the fact that we replace the PDE by a finite difference equation. All right? But the problem is compounded by the fact na, okay, meron ka ng discretization error dahil sa equation na yan. Ang isa pang problema ay si U upper J, hindi yan yung eksaktong temperature at time T sub J. Estimate lamang yan para sa temperature sa U upper J. So this guy is tainted by error, right? Tapos yung erroneous information na yon, ipa-plug in mo sa equation na to, so dadagdag yung error galing dun sa previous estimate, papatong siya dun sa error na manggagaling dun sa discretization. So kaya lumalala na lumalala or lumalaki na lumalaki yung error habang nagmo-move forward ka in time. So basically, that's what I was looking for, yung propagation ng error due to the use of estimates to get another estimate. Yun yung isang ina-avoid. Sana wag tayong gumamit ng estimate kung meron namang paraan para makakuha tayo ng perfect data or true information, all right? At gagamitin natin sa formula, yun yung gawin natin. I-avoid natin yung paggamit ng estimates. Kasi magpa-propagate forward yung error mula sa isang estimate kapag yun ang ginamit mo para kumuha pa ng isang estimate. And one of you had a good analogy, or have a very good analogy for it. Sabi niya, sir, parang ano yan, parang naglaba ka ng damit. Alright? So, limbawa, meron kang first batch ng nilaban, naglaba ka, and then, assuming perfect yung pagkakalaba mo, napakalinis nung damit na magiging output dun sa process ng paglalaba. Pero halimbawa, hindi mo tinapon yung tubig. Doon ka naglaba ng second batch. So we do not expect that the second batch will be cleaner than the first batch kasi tainted na yung ginamit mong information, which in this case is yung water, doon sa second batch kaysa doon sa first batch. And I really appreciated that analogy. I just forgot who was it. Yeah. And one thing na napansin ko ay may mga gumamit ng term na truncation. Sabi nila, sir, ang problema dyan, kasi dun sa pag-compute kay use upper J, meron ka ng truncation or nag-truncate ka na ng values o nag-truncate ka na ng decimal digits, tapos yun yung ginamit mo para makuha si U upper J plus 1. Okay? I know what they are trying to say, or at least I want to believe that I know what they're trying to say, which is essentially the idea of there's an error in U upper J and you are using it. You're using effectively an erroneous data to get U upper J plus 1. I know that's what they are, yeah, I know that's what they are trying to say. Pero gumamit kasi sila ng term na truncation. Iba yung term na truncation. Pag sinabi mong truncation, pinuputol mo yung isang mahabang number. Halimbawa, meron kang number na 3.14, 15, 92654, tapos, and so on, which is the approximation for pi. Pag sinabi nating truncation o nag-truncate ka ng value, puputulin mo lang to sa number of decimal digits allowed. Right? So, iba yung error na nangyari dun sa U upper J. Siya yung discretization error o siya yung theoretical error due to the approximation method that we chose. So the right term there is theoretical error or the global discretization error na i-discuss sa 175. All right? Pero hindi siya truncation, all right? Though truncation might play a role kasi sa computer natin pinagawa yung computations, pero hindi yun yung main driving force doon sa error. So Kahit alam ko na yun yung gusto nilang sabihin na nagpapatong-patong yung error galing dun sa previous estimate sa ginagamit mo para makuha yung bagong estimate, nag-minus ako. Kasi be careful with the technical terms that you are using. If you're not familiar or too sure with a certain term, then don't use it. All right? Unless yun yung pinapa-define. If you can circumvent and just use terms that you know for sure what they meant, yun na yung gamitin nyo. And I'm not looking for highfalutin statements, So basta na-explain nyo in your own words, okay na ako doon. Masaya na ako doon. You don't need to impress me with jargons and so on. All right? Actually, pag nag-grade ako ng kahit ano, I'm looking at it from a non-specialist point of view. Kunwari, wala akong alam. Or, hindi. Kunwari, napaka-basic lang no alam ko. Rudimentary math lang yung alam ko. So, pag nagpapa-essay ako, nagpapa-explain ako ng solutions, gusto kong i-treat nyo ako as isang normal student, no? Na kailangan explain sa kanya bawat step. So don't use big words if there's no need to use big words because pag nagkamali kayo ng gamit ng isang technical term, maminusan ko kayo. All right? It's better to use simpler words and simpler sentences. Okay? Hold on. Umatake na naman yung runny nose ko, guys. Hold on. Okay, so going back to our discussion, so tapos na yung mahabang patalastas. So let's continue. We are discussing the L curve, which is one of the most basic routine that you can implement to get the Tikhonov solution for a linear system, right? So if you have the linear system, AX equals B. Okay, so mhm. Hindi na nagmo-move yung screen ko. Hold on, guys. Let me start my share screen again. Habang inaantay ko to, any questions about those submissions that I returned? Clarifications? Wala naman? Okay. Now, so let's quickly recap what we did last time. So we look at linear systems AX equals B. All right. But actually, in reality, hindi to AX equals B. Ang sinosolve natin ay AX equals true data plus epsilon, right? So we are imagining AX equals B to be our exact equation. Pero yung B natin dito na right-hand side, hindi siya yung perfect data D. Siya ay data plus measurement error or data noise, right? So yung naive reconstruction na tinatawag natin, or dalawa yatang dot yung nasa taas ito. So yung naive reconstruction could either be the direct inversion method or solution, wherein we have x equals A inverse B if A inverse exists. All right. And or if A inverse doesn't exist, we can use the least square solution. Our least square solution is x equals A conjugate transpose A inverse times A conjugate times B. All right. This is what we call the least square solution. Meaning kung hindi kasi invertible si A, posibleng walang eksaktong solution yung equation AX equals B. Now, the next best thing to an exact solution is the least square solution. Or actually, this is the next best solution in terms of the L2 norm. So itong least square solution o yung tinatawag din natin na normal equation, siya yung solution na may pinakamaliit na L2 norm ng residual. So this is the minimizer of the residual norm with respect to the L infinity norm. Okay? So siya yung may pinakamaliit na error with respect to the L2 norm. So, and then you can also think of it as the Moore-Penrose solution. This is A pseudo inverse times B. All right. If A is invertible, then these two guys must be equal to each other. So there should be no problem with that. All right. Now, this would have been perfect if your right-hand side B is perfect data. Or yeah, you don't if you don't if you're not worrying about measurement error or noise in the data, sure ka na yung right hand side mo ay walang error, or hindi ka naman nasa physical application na yung parameters mo dun sa problem ay posibleng magkaroon ng little errors, right? Kasi ang titingnan pa nga lang natin dito ay noise dito sa B. Paano na kapag meron ka ng noise kay X? Ibang usapan pa yung noise kay X. But if you don't expect to have noisy right-hand side, or you don't expect production error dun sa kay X, meaning kung application to, mare-reproduce mo ng eksakto si X. Pero paano kung si little x ay measurements din yan? Kung ang nire-represent ni unknown x ay mga measurements, then kailangan maging wary ka rin with what we call the production noise or the manufacturing noise. Halimbawa, dun sa example, halimbawa, ang x mo na-compute mula dun sa linear system ay 1, 1. Kunwari, ito ay measurements, 1 meter at saka 1 meter, right? Kapag in-implement mo na yung solution sa isang physical setting, imposible na ma-produce mo yung eksaktong 1 meter by 1 meter na vector x. Kasi nga hindi perfect yung measurement devices. So yung x mo ngayon na ma-manufacture mo or ma-physically instantiate mo, may error din yon kasi nga hindi perfect yung measurement devices. So instead of 1 meter by 1 meter, which is dictated by your solution, baka naman ang makuha mo ay 1.01 by 0.99 kasi nga merong kaunting error yung measurement mo. Alright? So yung tinatawag ng manufacturing noise, which will also tell you na to be wary noong naive solution. Na yung naive solution, hindi siya sufficient. Kasi pag konting nabago yung right-hand side, mababago totally yung solution. Or kapag nabago ng konti yung solution, may iba na yung right-hand side vector mo. Right? Hindi mo makukuha yung eksaktong B from AX equals B if X is tainted by data. Right? Kasi nga lalo na kung ito ay galing sa inverse problem. So if those cases arise, then sabi natin meron tayong tinatawag na Tikhonov regularization or the Tikhonov solution. Sa Tikhonov solution, hindi lang natin minimize yung residual. Ito yung ginagawa natin kapag least square solution. Minimize natin yung L2 norm ng residual. Pero sa Tikhonov solution, which is highly recommended if you expect data or noise in the right-hand side, or you are expecting manufacturing error, right, in terms of the reconstruction of X, ang kailangan mong i-minimize instead ay meron ka pa ditong plus, so pwede mo itong i-square, plus alpha times the norm of x squared, right? So meron ka ng extra term, and this term will take care of the sensitivity, all right? So ito yung tinatawag natin na residual norm squared, okay? Kasi ang residual norm lang ay yung walang square, all right? Yan lang yung residual norm. And this is what we call the solution norm, okay? So minimize din natin yung solution norm. Kasi yung pag malaki yung solution norm, ang laki ng posibleng sensitivity doon sa solution na makukuha mo. So we want to find the perfect balance between the residual norm and the solution norm. And we can do so by choosing the optimization parameter nicely. Not optimization, the regularization parameter. Regularization parameter. Okay. At yung pinakamadaling paraan para makuha yung regularization parameter alpha ay yung paggamit ng L-curve. Pero naikwento ko na sa inyo last time, medyo magastos yung pag-i-implement ng L-curve solution. Alright? Para makuha yung optimization o yung regularization parameter. But I think I promised you last time na bibigyan ko kayo ng code kung paano natin makukuha si alpha. Alright? And that's what I'll share to you in my next screen. Tanggalin ko na muna itong slides natin. I guess I solved the problem kasi kung matatandaan nyo, nagmi-misbehave or nag-underperform yung Matlab ko. Kailangan ko lang yata palang mag-update ng Windows. So, medyo mas okay na siya ngayon kaysa the last time, before I updated my Windows. So I shared with you the L-curve sample.m, which is the program I also shared to my 174 students. Medyo binago ko lang yung lines 5 to 8 kanina. Pinaghiwalay ko lang sila ng konti. This code replicates yung nandun sa ating module. Ito yung example Ito yung ginamit ko para i-solve yung example 9.5, right? So, in-implement ko siya dyan. Now, if you look at this, so yung first few lines will be initialization of the problem parameters. So, nilagay ko lang si matrix A, tapos yung right-hand side B, tapos nilagay ko yung error vector dun sa example, tapos papalitan ko ngayon yung right-hand side ng AX equals B by B plus E. Alright? Para makuha ko yung noisy solution. Okay? Now, we can actually, hold on, yeah. Let me just clear my workspace kasi meron akong mga variables pala kanina galing dun sa previous run ko. So clear ko lang para mawala yung variables dun sa aking workspace. Tapos halimbawa, i-run ko tong lines sa 5 to 8. So makukuha ko yung data para dun sa ating specific problem. And I've mentioned na malalaman mo or magkakaroon ka ng rough idea if your problem is very sensitive to measurement noise or to perturbations to the right-hand side. And that is by looking at the condition number of the matrix A. Here we have what? We have a 3 by 2 matrix A. Maliit pa tong system na to, pero if you compute for its condition number, and you can do so by putting cond, C-O-N-D of, that's open parenthesis, then A, then close parenthesis, either at the command window or you can insert it as a line in your code. Sabihin niya na 629.5801 yung condition number. And remember, the condition number is the constant of proportionality doon sa relative difference between the true solution and the noisy solution. When I say noisy solution, that's the solution from the noisy data and the size of the error. All right, because if you look at the norm of the error vector, so norm of E, di-divide ko lang siya by norm of B para malaman ko yung relative size ng error vector natin. B minus E pala kasi yung B ko na ngayon ay na-update na to B plus E. So 1.05% yung aking measurement, yung size ng aking noise. So yung 1.05% na noise na yon, sabi nung isang remark dun sa module, it can cause condition number of A times the size. So makukuha ko ay 6.5956. So ibig sabihin yung relative difference between the true solution and the noisy solution will be around 660%. Or at most 660%. So ito yung nakita na natin dun sa handout, dun sa module natin. So the condition number gives us an idea na napaka-sensitive na itong problem na to sa measurement noise. So kailangan I need to be extra careful. Kahit hindi to nanggaling sa inverse problem, alam ko dapat na kailangan maging careful ako sa right-hand side. Okay, or perturbations in the right-hand side, which can the effect of which can be mitigated by using the Tikhonov solution instead. Okay, so yun yung gagawin natin dito. And then, so what I do is implement the L curve, and for that I need a mesh of alpha values. So ito yung mga candidates para dun sa ating alpha, yung nasa line 11. So dito, ang alpha ko ay isang vector mula kay 10 to the minus 16, right? So ito yung starting value niya, 10 to the negative 16. So we know that alpha is a very small number, so you could have started at 0. Pero alam ko kasi machine precision is around 10 to the minus 16. So virtually, kino-consider ni machine na 0 yung mga numbers sa kanyang computation, within computations that is less than 10 to the minus 16 or so, right? Minsan tumataas yan. Minsan 10 to the negative 20 kino-consider pa niya. Pero just to be safe, 10 to the minus 16 ako mag-start. Kasi anything less than 10 to the minus 16 can be thought of as virtually zero with respect to the double precision standard. Okay? So kaya mag-start ako ng alpha candidates mula sa 10 to the minus 16. Tapos to get to the next alpha candidate, ang step size o ang increment ko kay alpha ay 10 to the minus 6. Now, if you think your computer cannot afford too dense mesh for alpha, taasan nyo tong increment na to. So instead of 10 to the minus 6, you can try 10 to the negative 5 or 10 to the negative 4. Para kakaunti lang yung mga excess na o yung mga alphas na chine-check nyo. Alright? And then ang upper bound ko ay 1. So ito yung pinakamalaking posibleng maging value ni alpha. Pero pwede nyo itong babaan. Actually, pwede nyo itong gawing 10 to the minus 3 na lang. Okay? Kasi, or 10 to the minus 2. Kasi hindi na, si alpha isang number that is much less than 1. Alright? So just to save on computational resources or to save time, huwag niyo nang paabuti ng 1. Kasi most likely naman yung alpha ay isang number na mas maliit sa 0.01. Okay? So kaya pwede niyo itong putulin na sa 10 to the negative 2. So mas kakaunti ngayon yung iraran nyo. Right? So those are some tips on how you can save. Or you can just, pwedeng palitin mo yung upper bound, laruin mo tong lower bound, saka laruin mo tong increment para dun sa pag-consider mo ng alphas, right? So let me see. If I do this, balik ko na lang muna sa 1 para totally ma-replicate natin yung nasa module. I run it, and if you look at the workspace, ilan to? 0. Yeah, I have 1,000,001 possible alphas. So medyo madami, medyo mayabang yung computer ko. Papatry ko sa kanya 1,000,000 at isang alphas. All right? And this is why this is a very expensive routine. Because kailangan ko ngayong isolve yung solution sa bawat isang alpha. All right? So here, I am just iterating, solving the Tikhonov solution for the 1,000,001 alphas that we got from line 11. But again, you can decrease that number. You can just consider 10,000 alphas, all right? Para mas mabilis yung proseso. Pero kung kaya naman ng computer nyo, why not? You might get a better alpha than using less candidates. The more candidates, the better. Para mas marami tayong option. So yeah, yung lines 14 to 18 implements the Tikhonov solution for every alpha. So nakikita nyo na trial and error ito. Sinosolve ko siya sa lahat ng possible sa mga candidates for alpha. Tapos doon na lang ako pipili sa mga kandidato na yon kung sino yung magiging solution. All right. I stored the Tikhonov solutions for all alphas in the vector temporarily in the vector X test. So si X test, hindi ko na isa-save yung 1,000,001 na mga X alpha, na mga Tikhonov solutions. Kasi pipili lang naman ako ng isa, di ba? Pagka sinave ko pa yan, bawat isa ay vector, mangangailangan ako ng malaking RAM. So to save some memory, nag-create lang ako ng isang dummy variable, which is X test. All right? So si X test ay dummy variable. Ang laman niya yung Tikhonov solution for a specific alpha, for one of the alphas. Tapos, instead of storing X test, ang gagawin ko na lang, ang i-store ko na lamang ay yung mga necessary information that we need from that X test, right? Remember, ang L curve, ginagraph lang natin yung solution norm versus yung residual norm versus the solution norm. So, hindi ko kailangan makita ano yung itsura ng mga X alphas o ng lahat ng X alphas. Kailangan ko lang i-save kung ano yung solution norm at ano yung residual norm para sa bawat alpha. So that's why I have line 16 and 17 inside the for loop. Yung line 16, kukunin niya lang yung solution norm, all right? How big is the solution X test, right? So yun yung isa-save niya. Ito yung norm ng solution X sub alpha. And note here, nag-save ako sa isang vector sol norm. So si sol norm of I. So ngayon, ini-store ko na lahat ng mga solution norms. Pag tinanggal ko yung I, edi magpapatong-patong lamang sa variable na scalar yung mga solution norm. Pero gusto ko kasing store lahat ng solution norm para sa lahat ng alpha, so kaya dapat naka-vector si sol norm. Ang ith entry niya ay yung solution norm ng ith na x-test. Pero wala na tong ICX test kasi ayokong isave lahat ng X test sa bawat iteration. Ang kailangan ko lang talaga makita ay yung solution norm, which is in line 16, at yung residual norm, which is at line 17. So in the end, after this for loop, I will have two important vectors. The vectors of the solution norm and the vectors of the residual norm. Okay? Tapos sabi ng L-curve technique, ipa-plot natin yung residual norm as the X components and the solution norm as the Y components. Yun yung gagawin nung lines 20 to 24. Okay? Pwede ninyo nang burahin yung line 25, wala yung gagawin. So, experiment lang to nung sinulat ko yung code. So, yan. Anong ginagawa ng lines 20 to 24? Ipla-plot niya lang yung L-curve. Line 21, gagawa lang siya ng full screen na figure window para malaki yung graph na makikita natin. Kailangan ko yan kasi ito yung figure ng L-curve. Dito ako pipili ng point. Okay? Tapos, ano yung i-graph? Ano yung command para mag-graph? Ang ginagamit ko ay yung line 22, which is the log-log plot. Ibig sabihin na lang log-log plot, para siyang plot, PLOT, na usual plotting natin o scatter, parang yung plot ng isang graph na interpolated, yung graph magiging continuous yung graph. Pero kapag ka log-log yung ginamit nyo, katulad siya ng plot, pero ang gagawin niya ay yung x-axis at saka yung y-axis, logarithmic yung scale. So makikita nyo mamaya sa x-axis 10 to the something, yung scaling, tapos ganun din sa y-axis. So log-log, ibig sabihin logarithmic yung scale sa x-axis, logarithmic yung scale sa x-axis, sa y-axis. Tapos yung lines 23 to 24, ipa-plot niya lang yung, lalagyan niya lang ng label, yung x and y axis, right? So let's try to let's run this segment of the code. So run ko lang to. Of course, if you already know how this program works, you can just press F5, mag-run na yung buong codes. Pero inisa-isa natin para maintindihan nyo kung para saan yung bawat line. Kasi pagka in-implement nyo to, pwede nyo i-copy-paste yung part ng code dun sa sarili nyo yung code na mag-solve ng isang specific problem. So in your project, kasi i-require ko kayo na mag-regularization para sa isang inverse problem, hindi pwedeng naive reconstruction lang, kailangan nyo ng L-curve technique. So kaya magagamit nyo itong M-file na shinare ko kasi naka-program na generic para sa isang generic na function. Okay? So now I have figure 3 on my window. It's full screen as expected because the figure command comes in with some parameters that forces the figure window to be full screen. Tapos makikita nyo, tingnan nyo yung x-axis. Oops, mali yung, yeah. Tingnan nyo itong x-axis. It's from 10 to the negative 2 until 10 to the 0 nga ba yan? Haharang si Teams. Yes, 10 to the 0. Logarithmic yung scale niya. Hindi siya yung linear scale na 0.01 hanggang 1. Alright? So, ang scaling niya ay logarithmic para mas makita natin yung salient features ng graph. Okay? Yung y-axis, supposedly, if possible, magiging logarithmic din yan sana. Pero dahil yung values lang nung solution norm ranges from 0 until 7 point something, hindi maganda, sabi ni Matlab, hindi maganda na mag-logarithmic plot ka dyan. So kaya yung ginawa niya, linear yung scaling. So siya na yung nag-decide para sa atin. So but this is, I guess, the best figure. So recommended na gumamit ng log-log plot para dun sa ating L-curve. Alright? Now, sabi natin, in principle, ang pipili nating alpha ay yung nandito sa corner. Because that alpha represents the best balance between the residual norm and the solution norm. Because the more you go to the left, the more accurate the solution is, right? So habang nagka-traverse ka dun sa iyong curve, papunta ka sa kaliwa, paliit ng paliit yung residual norm. Ibig sabihin, paganda ng paganda yung accuracy nung estimate mo, right? However, kapag ka naman ikaw ay pataas ng pataas, lumalaki naman yung solution norm. At pag lumalaki yung solution norm, nagiging mas sensitive sa perturbations ng right-hand side yung ating solution. So you don't want to go too high or too much to the right. So ang perfect balance talaga rito ay itong nasa corner point. Ibig sabihin kasi this is a point of inflection wherein tingnan niyo yung napaka-steep nung change dun sa solution norm. Ibig sabihin, mag-sacrifice ka lang ng konti sa accuracy, ang laki na nung jump na mangyayari dun sa solution norm. So you give up or you sacrifice that little accuracy para makagain ng stability in the solution. Pero once you get here, pag nandun ka na sa corner, titigil na yung significant changes in the solution norm. If you go a little to the right, ang unti na nung nababawas dun sa solution norm. So parang ang idea doon ay hindi na worth it na mag-sacrifice ka pa ng accuracy. Kasi pag nag-sacrifice ka ng accuracy, napaka-konti na lang na nag-gain mo na stability. Unlike kung nandito ka, dito sa medyo taas, pag nag-move ka ng konti pa kanan, ibig sabihin nag-sacrifice ka ng kaunting accuracy, ang laki nung nababawas na solution norm. Ibig sabihin, ang laki nung nagigain mo na stability. Kasi ang steep ng curve na to. Pero pag nandito ka na, sa kanan na ng corner, pag nag-move ka sa kanan, halos wala ng improvement dun sa solution norm. So, pag nag-sacrifice ka ng accuracy, baka hindi na worth it yung nagigain mo na stability. That's why you want to choose the corner. Kaya lang, how do we decide, how do we extract the necessary information? Oh, but in the first place, what's the necessary information that we want to get? We want to get what's the alpha that gave us the corner point. But if you look at the graph, pagka nag-hover ka dyan, tapos iniwan mo yung mouse mo dun sa corner, alright, ibibigay niya yung coordinates ng point na yon. So, ibig sabihin, itong corner point ay nasa 0.0347006, right? And then y is 1.388. But what are these numbers? Yung x value, siya yung residual norm. Ibig sabihin, kung ito ay nanggaling, yung point na yan ay nanggaling dun sa solution ng L2 norm noong kanyang error ay 0.0347. Tapos yung y component siya naman yung solution norm. Ibig sabihin ang norm ng solution dito ay 1.388. But I need neither the residual norm nor the solution norm. So wala dito sa information na to yung gusto ko, yung kailangan ko. Ang kailangan ko ay ano si alpha na nagbigay sa akin ng solution na yan. Sino yung alpha that gave us a residual norm of 0.034 and solution norm na 1.388. Yun yung kailangan ko ngayong i-trace. Sino yung alpha na yun? Kaya lang sa graph na to, tinanggal ko yung information about alpha. Alright? Now, a remedy to that is the following lines in the code. Tingnan natin yung lines 26 until 30. Okay? Ito yung naisip ko na paraan. There are some algebraic way to find or calculus-based method to find the alpha. You can search the literature. Maraming mga research papers na nagbibigay ng paraan paano mahanap yung corner point ng L-curve, right? But that's a little bit of more discussions kung titingnan pa natin. But you're free to look for it. Pero ang simple kasi ng problem eh. Hanapin mo lang yung... Kailangan lang natin malaman sino yung alpha na nagbigay dun sa corner. Kung napakalaki ng problem or gusto mong i-automate fully, kung lagi mo itong gagamitin, kailangan mo ng, syempre, algebraic way to find alpha. Ang ginagawa ng iba, minimize nila yung curvature o kino-compute nila yung inflection point. So, ibig sabihin, the choice of this corner point depends on the second derivative of the function, the solution norm as a function of the residual norm. So, kailangan mong express analytically ano si solution norm in terms of the residual norm. You take the second derivative, you do some minimization on it, or to some version of that. Essentially, magbo-boil down talaga siya sa second derivative ng solution norm. I don't know how that looks like, pero it can be done. All right? Doon mo mahanap yung corner na yan. Pero ang problema, medyo komplikado yon, and it is subject to further research. So kailangan ko na lang ng isang clever way on how to extract that information. And what I thought of is use the G input command ni Matlab. Yun yung nasa line 27. Now, the G input is a command for using as input the point on the figure that the user will click. Okay, so nilagyan ko siya ng comment dito. So pag niran nyo to, pag niran nyo yung line 27, kasama nung lines 20 to 24, all right? So, mari-require kang ngayon na mag-click doon sa L-curve. I-click mo si L-curve, kung ano yung i-click mo, isa-save ni Matlab kung ano yung XY point na kinlik mo. All right? Tapos, kapag ka na-save ko na yung X and Y coordinates, ang papagawa ko kay Matlab ay hanapin mo pang ilang element ng solution norm vector yung na-click ko. Alright? So kasi si G input, so magkiklik ka, ang return ni G input ay two vector, yung X component at saka Y component nung point na kinlik mo. Ngayon, ang gagawin ko ay, una, i-check ko muna kung yun yung, i-check ko kung ano yung absolute value ng solution norm minus xy2. Meaning, this is the second coordinate nung kinlik ko na point. The second coordinate of the point that I click represents the solution norm. So, ibig sabihin, titingnan niya lang, ima-minus niya yung y coordinate, the second coordinate, yung xy2, at yung second coordinate na nakuha kay G input, ima-minus ni Matlab siya dun sa solution norm vector. So sa solution norm vector, siya yung vector na laman lahat ng solution norm. Sa lahat ng entries ni solution norm, ima-minus ko yung y component nung na-click ko na figure. Right? Para si test vector, laman niya ay gaano kalayo yung solution norm dun sa desired ko na solution norm. As ang gagawin ko ngayon, hanapin ko sino yung pinaka-swak doon sa na-click ko na point. Sino yung pinakamalapit na y-coordinate doon sa kinlik ko na point. Yun yung gagawin ng line 29. I-assign ni Matlab yung variable na or the coordinate para dun sa pang ilang entry or ano yung coordinate doon sa solution norm vector noong nagpalapit kay 0 nung test entry. Remember, si test vector, laman niya yung absolute difference ng sol norm minus yung kinlik ko. Ang goal nun ay mahanap ko sino yung pinakamalapit na solution norm dun sa solution norm nung point na kinlik ko. Alright? So ang gagawin ni Matlab, hanapin niya kailan naging minimum yung entry ni test. Ano yung coordinate kung saan nangyari yung pinakamaliit na entry ni test. Kailan nagiging minimum yung entry ni test, nagiging minimum yung entry ni test pag super lapit nung solution norm on the ith entry doon sa na-click ko na y component. Alright? So tapos sasabihin ni Matlab, hanapin mo pang ilang, sabihin natin kay Matlab, hanapin mo, isave mo kung pang ilang entry ni solution norm nag-occur yung minimum nung test entry o nung entry sa test vector. Yun yung tatawagin nating coordinate. And that coordinate, yung magsasabi sa atin na pang ilan doon sa alpha vector yung nagbigay sa atin ng best solution. Alright? So kasi di ba nagba-match yun? Kung nasa ith alpha ka, alright? So makukuha mo yung ith entry ni sol norm at saka ith entry ni residual norm. So ang ginagawa, nung line 29, hinahanap niya sino yung solution norm na pinakamalapit dun sa kinlik ko na y component. Alright? At i-return niya kung pang ilan dun sa solution norm. Sabi niya pang ilang entry dun sa solution norm vector, yung pinakamalapit doon sa kinlik ko na y component dun sa figure. Okay? Tapos save niyo yun as coor. Tapos sabihin ko, si optimal alpha, which I will call alpha opt, ay equal doon sa alpha of 1 comma coordinate. Alright? Remember, si coordinate, siya yung magsasabi pang ilan. Kasi si alpha ko ay ay row vector. So, ang i-assign ko to be alpha optimal ay yung entry ni alpha vector on the first row cohort or yung pang-cohort na column. Okay? So, tingnan natin kung ano yung mangyari. Actually, yeah. Let's see what happens. So, i-run ko ng sabay yung, hindi. I-run ko simula line 20 hanggang line 30. Okay? I'll press F9. So, lalabas uli yung figure. Tapos naka-G input na to. So makita, alam nyo na naka-G input kayo kapag ka may target na lumabas sa itong criss-cross na to. So lalabas siya. Ibig sabihin, nasa G input command kayo. Gagawin nyo lang, use your mouse or your mouse pad. Tapos i-click nyo yung corner. I-click mo lang yung corner. So kaya gusto ko full screen para mas precise yung pag-click-click ko ng corner. So I'll click it. Okay? Mawawala yung crisscross. Ibig sabihin, na-save na ni Matlab yung kinlik mo na point. Tapos, balik ako kay Matlab. Okay? Meron akong alpha opt. So, yung alpha opt, or muna yung alpha opt. Tingnan ko muna yung coor. Yung coor, 1049. Ibig sabihin, yung pang 1049 na alpha, siya yung nagbigay sa atin ng y-coordinate nung kinlik ko na point doon sa L-curve. Alright? So ngayon, si alpha opt, siya yun yung pang 1049 na alpha. At yun yung 0.001. Tama ba yun? Parang iba to dun sa, hold on. Pinago ko nga ba to? Parang iba to dun sa alpha na nakuha natin kanina. Nakuha dun sa handout. But anyway, let's see what the result would be. Now, si lines 34 to 39, i-check niya lang kung na-generate ko yung corner point. Alright? Kung tama yung na-click ko. Pan-double check lang, sanity check. So, I'll press F9. So, kung makikita nyo, merong orange or red dot. Ibig sabihin, ito yung kinlik ko na alpha. Alright, ito yung naging result ng G input. Which is fine kasi medyo naman to, medyo malapit dun sa corner. Alright? So, pwedeng magkakaiba tayo ng kaunti ng alpha depende dun sa precision ng pagkaka-click nyo. Pero makikita nyo dito sa result ng lines 34 to 39 kung gaano kalapit sa corner yung chinek nyo. So, kung satisfied kayo na, okay, tama yung kinlik nyo kasi napakalapit sa corner, then you're good. Alright? I-reconstruct nyo na uli yung solution. So that's what I did here in lines 41 to 44. All right. So solve ko ngayon si X alpha. Now our X alpha is the Tikhonov solution using the optimal alpha. So remember, it's alpha optimal times the identity matrix of the appropriate size plus A conjugate transpose times A, tapos times A conjugate transpose times B. Tapos ipiprint ko lang ngayon yung relative errors. So let's see what happens here. F9. Oops, walang F solution noise. Bakit F solution noise yun? Para kasi yon sa para yun dun sa example ko mamaya. Alright, dun sa convolution. So, just forget about line 44 for now. Yung result ng line 43 ay itong nasa command window. The relative error with respect to the noisy data is 3.46% or 3.46 times 10 to the negative 2. So, ito yung accuracy ng solution natin. So, remember, the least square solution has relative error 0.56%. Pero sinacrifice ko yung counting accuracy. That's why I got here 3.46% na lamang. Okay. So that's how we implement the L curve technique. Though I don't think I replicated exactly what was in the handout, ano. So but you can try. Siguro hindi maganda yung pagkaka-click ko dun sa L curve because if I'll go back to the example, dapat ang alpha ko ay 7.81 times 10 to the negative 4, but my optimal alpha is 0.001, right? Right, kaya 0.001. Yeah, let me just rerun this again and see if I can better replicate the solution. Okay. Tapos, i-click ko to. Naka-G input tuloy ako. Click. And then, okay. So this is my checker. Magpa-pop up bigla yung checker is sabi niya, okay, around nandito yung kinlik mo na point. There you go. Sorry, hindi pala, iba pala to. 3.48% pa rin yung nakuha ko. Yung nasa handout ay dapat 1.03%. So somewhere to the left pa. Or did I mess up my computations here? But anyway, that should be it. Baka lang hindi ko na-click ng maayos kasi here, my alpha optimal is 0.0021 pero dapat 7.81 times 10 to the negative 4. Ano kaya yung naging problema? Or maybe I used a denser mesh pero 10 to the negative 6 to 1. 10 to the negative 6 yung step size. Ang alpha ay 10 to the negative 4. Yeah, let me trace what happened. Ano, bakit hindi ko nakukuha yung 7.81 times 10 to the negative 4? But this is the same program I used to write the module. Ano? The only explanation I can think of now is baka iba yung na-click ko or mas accurate yung pagkaka-click ko dati pero masyadong malayo eh. So I'm not sure. I'll double check the given later, but yeah, but that's the idea. Okay. Now, any questions before we implement this for the for the convolution problem? Hold on, guys. I need to sneeze, so hold on. Okay, so I'm back now. CLC. Oh, I'm using the command CLC. Yung CLC ay para lang ma-clear yung laman ng command window. Okay, so press CLC, mawawala yung nasa command window, pero lahat ng variables na nakasave, andito pa rin sila. Okay? Pero sige na, i-clear ko na rin. Tapos magto-close ako ng mga figures. Close ko na nga lang lahat ng figures, so close all. Okay. Now, let's revisit the convolution problem that we have last time. Similar din dito yung ginawa niyo sa problem set. Ano? So meron tayong convolution ng alpha ko ay 0.04. Gumamit tayo ng 64 data points. Tapos if you run this psf.m na minodify nyo rin para sa problem set, medyo matagal. Ano? So if you want to save time, if you will be using this data and you don't want to do it over and over again, pwedeng isang run na lang. Tapos yung result, pwede nyong i-save. Right? You can put in the last line in your code or in the command window, pwede nyong i-type yung save. Tapos kung ano yung file name na gusto nyong ibigay sa kanya, halimbawa, enclosed in single quotes. Kasi pag single quotes, para malaman ni Matlab na string or character, yung type of data na ginagamit mo. So rito, iti-treat ni Matlab na string of characters yung data.mat. Right? So pag pinrest niyo yung save of data.mat, is-save ni Matlab lahat ng variables dun sa workspace nyo in the file data.mat, data.mat. Alright? Para lahat ng resulta, lahat ng lumalabas sa workspace sa isang niranyo na Matlab command ay masisave din sa data.mat. Alright? Ngayon, wala nga lang laman yung data.mat pero save lang yan ni Matlab as an empty file. Ano? Mache-check nyo na na-save na pag pumunta kayo dito sa current folder sa leftmost panel, may makikita na kayo na data.mat. Okay? Tapos may preview ng laman ng data.mat. Ito namang nasa lower left portion. Tapos nakikita nyo, wala siyang laman kasi yung sinave ko na data.mat ay yung empty workspace. Alright? If you want to load the information from a mat file, gagawin nyo lang load. Tapos, file name. Pero yung file name ay dapat naka-enclose in single quotes kasi string of characters siya. Then press enter. Whatever the content of data.mat should appear in the workspace. Pero unfortunately, si data.mat ko ay empty, so kaya walang na-load dun sa workspace. Right? An alternative is you can double-click data.mat from the folder explorer dun sa leftmost portion. So ito, naka-highlight si data.mat. Double-click ko lang yan. Tingnan nyo, nalagyan ng load ulit. So, siya na yung automatically nag-type ng load command, tapos papasok na lahat ng mga variables na naka data.mat dun sa current folder. Okay? Now, I know by experience, alam nyo na matagal mag-run yung PSF kasi ang dami yung symbolic calculations. Nirun ko na siya kagabi or nung Monday, alright? Tapos sinave ko yung data, yung mga variables dito sa conv-data.mat. Okay? Pag kinlik ko si conv-data.mat dito sa folder explorer, makikita nyo na populate yung lower portion. Ito yung mga variable niyang laman. Alright? So ito lahat ng resulta ng calculation ng PSF. May last calculation ng PSF. And I'll just double-click conv-data.mat, okay, para ma-load. Or you can type load in the command window, or you can put this command inside your Matlab code. That's also fine. Para F5 lang yung i-press nyo. No? Pero yan. At makikita nyo sa workspace, andito na lahat ng mga variables na kailangan ko. Yeah, this makes plotting the graphs easier because hindi ko na ngayon kailangang i-compute. Kasi yung pagko-compute ng convolution, pagko-compute ng data, yun yung matagal. Kasi meron yung mga symbolic computations. May symbolic integration tayong pinagawa kay Matlab. Right? Pero ang kagandahan dito, nakasave na si matrix A, hindi ko na siya kailangang ipa-compute, tapos yung mga data nandito na rin. Okay? So let's recall what happened in this particular example. So, sinolve natin yung inverse problem using ang ginamit pa natin nun ay eksaktong inverse because we don't know the pseudo inverse yet ng mga panahon na yon. So you can replace this by pinv or you can replace it by a\data y prime. Okay? Okay lang din yon. Pero niretain ko na lang to. Tapos tingnan natin yung naging resulta with perfect data. So, irarun ko lang yung line 67 to 74. Ito na lang yung irarun ko kasi lahat ng value ng mga variables na kinocall ng line 67 to 74 ay nakasave na sa workspace. Na i-load na natin galing dun sa conv-data.mat. Alright? So, all I need to do is to press F9 or right-click and choose Evaluate Selection to Command Window. Okay. So, makikita ko, ito yung reconstruction natin from perfect data. Okay? Makita nyo, merong mga konting error dyan, alright? Pero this is fine. Kung gusto nyo makita gaano kaganda yung solution, well, kunin nyo lang yung relative error and I'll just do it in the command window. You can put it in your Matlab code. Kunin ko lang yung residual norm. So it is the norm ng F solution. Yun yung tawag ko dun sa solution na galing sa line 63 minus the actual vector f, yung exact solution. Ang tawag ko sa kanya dito ay f exact. Okay. Divided by the norm of f exact, malalaman natin yung relative error. So the relative error is, bakit ang laki ng relative error? F solution minus F exact, 5.81. Hindi ganun dapat kalaki yung error. Dapat ang error nito ay transpose ba? Let's see. F solution. Let's see. Baka nga. Yeah. Baka ito rin yung naging problema dun sa ibang mga problem sets, ano? Kasi dun sa problem set 1.1, siguro kinopy-paste nyo tong code ko. Hindi nyo napansin na may problema pala yung pag-solve niya ng solution norm. Thank you, sino ba yun? Si Neil. Si Neil yung nakapansin. Alright, thank you, Neil, for that. Yeah, kasi yung makikita nyo, si F solution dun sa workspace, 64 by 1. Tapos si F exact ay 1 by 64. So pag kinuha niyo yung F exact minus F solution, magkakaroon tayo ng 64 by 64 na matrix. So ibig sabihin ng kinompute pala na norm ay matrix na F exact minus F solution. Pero meron kasing mismatch doon ng dimension. Si F exact pala dito sa pagkaka-code ko ay 1 by 64, pero si F sol n ay 64 by 1. So yung F exact minus F solution, kinompute ni Matlab to be a 64 by 64 matrix. I'm just not sure how exactly Matlab carried this out, pero dapat undefined siya, right? Kasi ang matrix subtraction dapat same size. So, dapat tinranspose ko nga siya. So, baguhin ko lang. So, si F exact, gawin kong equal kay F exact transpose. Para si F exact ay maging 64 by 1 na din. Yeah, yun yung naging problema pala dun sa code ko. So, yeah, and then that also happened to, I think, 2 or 3 groups. Ang laki ng relative error na nakuha nila. Yung pala yung nangyari. Alright, akala ko may mismatch dun sa pagkaka-encode ng meshes. Ang mismatch pala ay dun sa dimension ng meshes. Alright? So ngayon, pwede ko nang computein yung norm. Dapat tama na to. Ayan, 14%. 14.36% yung error. Now, kaya ako nag-minus dun sa mga 500% yung sagot, ano? Ng medyo malaking points. Kasi dapat na-realize nyo na something is wrong. Because katulad kanina, right off the bat, kahit hindi ko alam kung ano yung error dun sa handout natin. Pag tiningnan ko yung reconstruction, halos magkamukha naman yung reconstruction, yung naive reconstruction natin kay F at saka yung actual solution, right? Of course, may mga deviation, but I doubt that those deviations cause the relative error to be around 500%. Hindi ko matanggap na 500% yung error, kaya i-debug ko yung program ko. Thanks to Neil, hindi ko na kailangang i-debug yung program. Napansin niya na to siguro nung nagpa-problem set na hindi na transpose ni sir. Yung isa, nagkaroon ng mismatch dun sa dimensions ng F exact at saka F sol n. Kaya nagkaroon ako ng matrix as my F exact minus F sol n. Yun yung problema kay Matlab. Adelantado si Matlab na nagkusa siyang mag-define ng 1 by 64 matrix minus 64 by 1 matrix naging 64 by 64. Pero dapat hindi nangyari yun kasi dapat pag nag-subtract tayo ng vectors, dapat same dimension sila. Alright? So yun yung indication na something must have been wrong and you should have debugged the program. Alright? So ngayon, mas tanggap ko na 14.36% yung error, yung relative error. Kasi almost magkamukha naman sila, so we get this figure. Okay? Tapos, tingnan natin yung noisy solution. Meron na akong noisy solution. Yung noisy solution ko, 1% yung relative size nung ating noise. Let's see, norm ng noise. Ang noise vector ko dito ay E divided by norm ng right-hand side vector B. Di nga ba yung tawag sa right-hand side? I think ang tawag ko sa right-hand side ay data y prime. Data y prime yung tawag ko sa right-hand side. So, kukunin ko yung norm ng error vector o ng noise vector divided by norm ng data y prime. And it's 1%. Right? So, 1% yung noise. Tingnan natin kung anong naging epekto niya dun sa solution. So, i-plot ko ito. Ito nga ba yung reconstruction? Yes, ito yung reconstruction. Pina-plot ko ngayon kay Matlab yung reconstruction with the noisy data. Makikita nyo, ang laki na naging epekto ng noisy data, right? Compared dun sa solution na nakuha natin from the true data. So the one on the left is what we got from perfect data. And the one on the right, ito yung nakuha natin from noisy data. Nakita natin medyo malaki na yung pinagkaiba. Okay? So now if we compute the relative difference between the reconstruction from the noisy data versus the true solution, tingnan natin yung relative error. So kukomputing ko lang yung norm. Instead ng F solution, gamitin natin yung F sol and noise. Ito yung noisy solution. Ito yung ginamit kong pangalan dun sa workspace. Tapos nakikita niyo 29.6% na yung error. So from 14% error, 14.36% yung error kung true data yung ginamit natin pang solve. Pero nung ginamit natin yung noisy data or yung data tainted by 1% noise as our right-hand side, we get a solution that is around 30% far off from the exact solution. All right? Medyo na doble. Ang laki nung naging epekto ng 1% noise. Yung 1% noise na yon caused the error to almost double from 14 point something percent up to 29.6%. So parang naging times 200% yung error dahil lamang dun sa 1% na noise. Right? And we could have had an idea about that if we computed the condition number of the coefficient matrix A. Ang condition number ni coefficient matrix A ay 176.11. So ibig sabihin yung 176.1172 na condition number, i-times ko siya by 1%. Ibig sabihin, posibleng maging hanggang 176% yung relative difference between the noisy solution and the solution from perfect data. So ito yung relative difference between what was the solution from the noisy data and from the exact data, right? So para ma-double check kung totoo tong upper bound na to, compute natin yung norm ng F sol n minus F sol n noise. So ito yung relative difference between the two solutions that we got, the one from the perfect data and the other one from the noisy data. Tapos medyo maliit lang naman yung relative difference nila, around 25%, all right? So pero malaki pa rin yung 1% na noise, nag-cause siya ng 25% different solution from the estimate we got from true data and the estimate that we got from the noisy data. And the one that we got from the noisy data is around 30% off from the true solution. Okay? Now, tingnan natin kung gagamitan ko to ng L-curve technique. Mapapaganda ba natin ng kaunti yung solution? So, pupunta ako sa L-curve sample, kasi irarun ko ngayon yung pertinent o yung mga relevant lines. Now, kung kayo ay gagawa ng isang program, you can take some parts of L-curve sample.m. Itong program na to, copy-paste nyo dun sa program na sinusulat nyo para sa problem set o para sa project nyo. Or you can translate L-curve sample.m into an internal function. Yun yung mas efficient. Gawin nyo tong external function kay Matlab. Pero hindi ko na siya ipapakita kasi ayoko nang mag-discuss ng programming. So kung nag-152 kayo, you have an idea how to use subprograms, external subprograms in particular. So pwede nyo tong isulat ng ganon. Alright? Para pwede nyo siyang i-call sa kahit anong program. Di nyo na kailangan mag-copy-paste ng mga lines. Alright? Pero ngayon, medyo simple programming lang tayo kasi hindi naman to AMAT 152. And some of you might not have taken AMAT 152, so hindi pa kayo familiar sa subprograms. Okay? But yeah, meron namang remedyo doon, ano? So hindi ko na ira-run yung lines 5 to 8 kasi si matrix A, yun yung nanggaling kay conv A, nakasave na siya 64 by 64. So hindi ko siya papalitan. Papalitan ko lang si B. Si right hand side B, gagawin kong equal siya dito sa hindi sa B plus epsilon, no? Gusto ko to ay yung noisy data. Punta ako kay psf.m. Tingnan ko kung anong pangalan ko dun sa noisy data. Ang noisy data ko ay data y plus plus noise vector e prime. So ito yung noisy right-hand side. Copy-paste ko lang siya sa command window. So si B ay papalitan ko ng value. Ang value niya dapat ay si data y plus e prime. Ito yung nanggaling na data dun sa psf.m. So ito, ina-assign ko yung right-hand side. Oops. Ano naging problema? Kasi may nakasave na value. Bakit meron dalawang doubles? Try ko ulit. Okay, there you go. Ni-read lang ni Matlab yung dalawang greater than. Kaya nagreklamo siya. Pero yeah, I let B to be equal to data y plus e prime, which is the noisy data from psf.m na nakasave. So meron na rin akong right-hand side B. And then you can check what's the size of, what's the norm of B with respect to the norm of, dapat pala ito ay noise, no? Ang noise natin ay E with respect to B, with respect to data Y prime. So 1%. 1% yung noise, that's fine, as expected. Tapos, sige, ano yung kailangan kong i-run? Kailangan kong i-run simula line 11. Kailangan ko ring i-run itong for loop para computein niya yung mga residual. Tapos kailangan kong i-run hanggang G input para makuha niya yung alpha, yung optimal solution. Tapos ito yung pan-double check ko, then the actual solution. Okay, so I can run the entire L curve sample.m except yung pagko-compute ng A, B, at saka E. So I'll press F9. It will take a little while because mas malaki ngayon yung matrix A. Yung matrix A ko ngayon ay 64 by 64. So, magreklamo yeah, that pala may pa-background music ako, no, habang nagsosolve siya. Kasi 1,000,001 to, tapos 64 by 64 na yung matrix natin ngayon, mas malaki na siya. So, mas expensive yung pagko-compute ng line, anong for loop. Alright? Kasi may 1,000,001 na elements, na iterations doon sa for loop. Tapos yung matrix na nandun sa for loop ay 64 by 64. So medyo mahaba-habang proseso ito. Sana matapos siya bago mag-dismissal. Sige, while Matlab is doing its job, any questions? I hope nagme-make sense yung program kasi pwede niyo itong gamitin sa project niyo. Bakit ang tagal? Okay, nagra-run naman siya. Para pala mas masaya dapat nilagyan ko siya ng ng progress bar, Meron na akong progress bar na ginagamit para malaman ko kung ilang percent na nung for loop yung tapos na, saka ilang percent, ilan yung ETA. Alright? Yeah, there you go. So ito na yung L curve. Sabihin niyo, sir, hindi siya mukhang L. Alright? And you're right. Pero inverted L siya. Alright? So, minsan may mga ganitong L curve yung itsura. Medyo nakabaliktad or naka-mirror image, Pero you need to interpret the axis, right? Ang alam natin, general principle, Habang pumupunta ka sa kaliwa, lumiliit yung residual norm. Habang bumababa ka, lumiliit yung solution norm. Right? So we need to find the balance between the two, right? If you look at the x-axis, ang liit ng residual norm. Ibig sabihin, we can get results that is as accurate as 10 to the negative 14. Pero we can give up much out of the 10 to the negative 14 to gain some stability in our solution. Okay? Yung solution norm, medyo malaki from 0 to 6 point something. All right? Pero yung residual norm, we can definitely give up something. All right? So, let's see. Now you have the degree here, the degree of freedom here, which one to choose. You can choose, kung super accurate nung kailangan mong result, you can choose this corner. Pwedeng yun nandito. Right? Kasi rito medyo meron kang sudden na pagbaba pagbaba ng solution norm. Pero makikita mo rito your residual norm. Kung titingnan nyo itong nasa x-axis, yung nai-hit ng aking target ay nasa malapit sa kaliwa ni 10 to the negative 2. So meaning if I click on this point, the residual error would be less than 10 to the negative 2. If that is good for you, if that's good enough for you and that's what you need, then you can click here. But you have another option. You can go a little bit to the right. Okay. Pwedeng ito yung i-click mo. Pero so here you get a big improvement in the solution norm. Kasi ang baba na ngayon ng solution norm. Look at the y-axis. So it's closer to 5.5 now than to 6. Pero pag tinignan mo yung x-axis, kung ano yung nai-hit ng vertical line dun sa nung G input, makikita mo, nasa pagitan tayo ng 10 to the 0 at saka 10 to the negative 2. So there's a chance that we are hitting 10 to the negative 1, which is 10%. So kung ayaw mo ng 10% yung error, so you can go a little bit to the left. So go a little bit to the left. Probably I'll choose this corner here. Or you can kung meron kang target na accuracy, pwede mo rin yung gamiting criteria pagpili nung gagamitin mong alpha. Halimbawa, ang gusto mong error ay hindi lalampas ng 1%. So ibig sabihin, dapat ang pipiliin mong point dun sa L curve mo, dapat ay mas maliit sa 10 to the negative 2 if your target is less than 1% error. So I'll click on here because halimbawa gusto ko 1% lang yung error or less. So this would be my choice of alpha. I'll click here. Okay. And then my checker, my sanity checker will give me another plot and will tell me, ito yung kinlik mo na point. All right. So babalik ako ngayon kay Matlab command window para makita kung ano yung alpha. Actually, na-compute niya na pala lahat. So here, the relative error with respect to the noisy data is 8.89 times 10 to the negative 3, or around 0.89%. Ito yung kanyang accuracy with respect to the noisy data. Pero yung accuracy niya with respect to the actual solution is around 7.49% or 7.94%. Right? Now, if I will assign this X alpha, tawagin ko itong X alpha, si X alpha siya yung tawagin kong F sol and noise ngayon, yung bagong F sol and noise. Remember, F sol and noise siya yung solution sa PSF.M with the noisy data. So, i-overwrite ko lang yun, sabihin ko si X alpha na ngayon, yung bago kong noisy solution. How did I spell X alpha? Okay, I think that's right. Okay, all right. Tapos ipa-plot ko ngayon, same plot with the one that we got in PSF.M. So ngayon ipapaplot ko na yung X alpha galing sa regularized solution versus the true solution, F9. Ito yung nakuha natin na reconstruction still from noisy data. Tapos i-compare natin to dun sa nakuha natin dun sa noisy data without regularization. Ito yung nasa figure 2. So yung nasa kaliwa, si figure 2, ito yung galing dun sa noisy data, pero hindi tayo nag-L curve. Pero tignan nyo, yung nakuha ko sa reconstruction, from noisy data pero gumamit na ako ng Tikhonov solution. Yun yung nasa figure number 5. Kailangan ko palang baguhin yung title. Hindi na to naive reconstruction. Ito na ay regularized reconstruction. Regularized reconstruction of F from noisy data. Kasi nag-L curve na tayo dun sa figure 5. And you see the stark improvement, nawala na yung yung medyo malalaking oscillation during this part and during this part. So napababa natin yung epekto ng 1% noise dun sa solution by just picking some alpha, right? Kasi compare natin to dun sa solution na nakuha natin from dun sa reconstruction natin from perfect data. Ito yung nakuha natin yung figure number 1, yung nasa kaliwa na ngayon. So makikita nyo, hindi na nagkakalayo yung ating reconstruction from true solution, from true data doon sa ating reconstruction from noisy data. So that implies that we have killed off or we have mitigated at least the effect of the 1% noise in our reconstruction. So medyo hindi na sensitive yung nakuha nating solution with respect to measurement noise. Okay? Now the challenge now would be to write a report summarizing all of these results that we got. All right. So siguro as homework, siguro homework worth 10 points. I will ask you to anong gusto nyong gamitin? Maliit na matrix na lang o yung nasa convolution? Maliit na matrix na lang para hindi masyadong matagal. Sige, I'll draw up a homework which will be due, sige, gawin kong due niya ay Friday next week. Bukas ko ilalabas yung homework para meron kayong 1 week to do it. Magbibigay ako ng isang matrix A, tapos papasolve ko siya sa inyo using perfect data. Tapos isosolve nyo rin siya using noisy data. So maglalagay kayo ng 1% noise. Tapos gagawa kayo ng mga figure na to showing the true solution versus the what do you call this? Versus the noisy solution, all right? Na galing sa naive reconstruction. Tapos i-apply nyo si L curve para makakuha ng regularized reconstruction. Tapos ipa-plot nyo side by side or i-copy paste nyo itong tatlong figures na to side by side. You have the naive reconstruction using the true data, the naive reconstruction using noisy data, and the regularized reconstruction from noisy data. And then ikukwento nyo ano yung relative error, ano yung relative difference, and so on. Okay? Okay ba yun? So that would be your homework for next week. All right? And then you can pattern the discussion from the one I have on the module. Or you can write it on your own way. All right? Doesn't matter as long as klaro sa akin kung ano yung nangyari. Okay? So, saktong-sakto 11:30. Sorry, overtime na naman ako. But I hope you got something today, especially the code. Kasi ito yung crucial. Kailangan nyo to para sa homework next week at para sa project nyo na rin. And actually, if you'll be doing an SP or a thesis in inverse problems, kailangan nyo yung L curve. Okay? So, any questions? Sir, wag na kayong magantay ng questions kasi overtime ka na. Tatakbo pa kami sa susunod naming face-to-face class, ano? So, yeah. Just let me know na lang if you have questions via email or chat me, ano? Expect the homework tomorrow. So then you'll have at least until Friday next week to submit it. Pero pwede nyo akong sabihan sa Tuesday kung kailangan nyo ng more time para gawin yung homework. I can extend the deadline of that particular homework to another weekend. Siguro pwede na, sige na nga, Monday next week na natin ipapasa, ano, for you to have more time to play with it. Then gagawin kong 10 or 15 points yung homework para medyo malaki siya. So pag-anuhan nyo siya, paglaanan nyo ng konting effort and ayusin nyo yung program kasi baka yung program na yun na rin yung gagamitin nyo para sa problem set. So practice siya para sa problem set. So, maliit lang yung matrix na gagawin nyo para mabilis yung computation. Pero marami kayong gagawin na programming kasi in preparation doon sa problem set number 2, nakakailanganin nyo to, pero totoong data yung paglalaruan nyo. So, ibig sabihin malaking matrix A yung paglalaruan nyo. Okay? So, I hope that's okay. And with that, thank you guys for coming today. Just let me know if you have questions, send me an email or a chat. Enjoy the rest of the week. And then let's see each other again on Tuesday. Right? Bye, guys.
Thank you po, sir.
All right. You're welcome.
Thank you po, sir.
Mhm.